Now let us try to understand why do we require machine opcode table. So the input to the assembler is going to be the source code or source program. This source program will be written in low level language, and the low level language that we are considering is a hypothetical language. So the source program written using the hypothetical language will carry only instructions out of this set of instructions that we are considering in the machine opcode table. Now let us understand how a typical machine opcode table will look like. So let us consider we have instruction move R. So its class is imperative statement, and the mnemonic info is a pair of two fields, that is a pair comprising of two fields. First field is machine opcode and second field is the instruction length. Now some facts that we are considering over here. The instruction length for our hypothetical language instructions we are considering as length 1 for all the imperative statements. So how this machine opcode for move R came to be 04. So let us now refer to the machine opcode table that we seen in the previous slide. So the move R instruction is here. If you see the mnemonic info of the move R instruction, it is 04. Hence we are considering the machine opcode as 04. So this 04 will uniquely identify the instruction as move R. Now let us have another field like add. So again it is an imperative statement and the machine opcode is 01. Length by default we are considering 1 only. Now again refer to the opcode table and locate add instruction. Add instruction is here and its mnemonic info is 01. That is the reason we have written mnemonic opcode as 01. Next is the condition codes. Besides the instructions that we considered in the machine opcode table, that is imperative statements, declaration statements and assembler directives. Now besides this set of instructions, there are condition codes that we may find in the input program, and these are considered as condition codes. So total 6 condition codes we have, and specifically these condition codes you will find in one of the imperative statement instructions, that is branch on condition. So this is branch on condition instruction. So typically the branch on condition instruction, it works in combination with other imperative statement, that is compare instruction, that is COMP, compare. So typically compare instruction compares the values of two different values. In fact, let us assume compare a register, the contents of a register with the contents of symbol X. Okay, now we have certain possibilities while comparing these two values. Now depending on the type of condition, we are going to have the branch on condition. That is, out of these 6 condition codes, we will be using as an operand to the branch on condition instruction. Let us assume less than. So less than, comma, second operand, let us assume back. Okay, so this compare instruction will ask assembler to compare values of these two operands, that is a register and X. Further, branch on condition will let assembler know this is less than if the contents of a register is less than the contents of X, then if this condition holds true, that is less than a register, contents of a register are less than the contents where x is pointing. In that case, this condition will hold true, and if it holds true, it should move the control of the program to the back. Okay, so these are the 6 condition codes that we may find in our input program. So the less than, second one is less than equal to, third is equals to, fourth one is greater than, then fifth one is greater than equals to, and any means unconditional jump. Now for any operand, let us assume instead of this we have, let me change the color, we have branch on condition any back. So in that case, it makes no sense to compare the values. Rather, unconditionally, we will be jumping or we will be transferring control of our program to back. And it is obvious you will find the symbol back in the label field of any of the instructions in the program, and the control will be transferred to that particular instruction. Now next field in the condition codes table is mnemonic info. So while translating a program having the condition codes, we will be considering less than is condition code as its mnemonic info 1. So we will identify this less than as 1, less than equal to as 2, and similarly any as 6. So while converting this into 1, 2, 3, 4, 5 or 6, accordingly our assembler will understand 1 denotes the less than, similarly 6 denotes n. It will be more clear for us when we go through one of the examples, but right now we just need to understand we may find condition codes in the input program to the 2-pass assembler. Now next is symbol table. So symbol table is going to be the output of our pass 1. Now the typical symbol table will look like this, having 3 fields in it: symbol, address and length. So in our program, let us assume we have one of the symbols as loop. We will make entry of that symbol in the symbol table, and the current location counter is going to be the address of the loop and the length of the symbol that we will have in the symbol table. Although for us this third field in the symbol table, that is length, is not mandatory. So even if we skip writing the field of length in the symbol table, it's okay for us. Now how the symbol table is to be generated, that we will see once we go through one of the examples. Now second is literal table. It is again the output of pass 1 of assembler, and typical literal table, it looks like this, having 2 fields in it. First one is literal, second is its address. Okay, so let us assume in our program if we encounter the literal 5, we will make entry of that literal in the literal table, and once we assign the address or we allocate memory to this literal 5, so accordingly we will be updating its address over here. Okay, so how this address is to be generated or updated in the literal table, that will be clear once we go through the example. Now next is pool table. Pool table is again the output of pass 1 of 2-pass assembler. Now this pool table contains only one field, that is literal number. So this denotes the pool 1 of literal is starting from literal number 1 of the literal table. Similarly, pool 2 is starting from third literal in the literal table. Thank you. We will, in the next video, we will look at one of the example. of a 2-pass assembler.